Now, this series is about manifold, but in all the previous episodes we haven't heard the word manifold. It seems almost as if we were going on tangents because we were talking about vector spaces instead. But no, the discussion is very relevant because to every manifold we can associate a bunch of vector spaces that carry a lot of information, namely the tangent spaces. Since a manifold by definition is locally flat, locally Euclidean, it must locally look very much like its tangent space. Tangent spaces provide us with a way to linearize the manifold, and then that allows us to use tools from linear algebra to give geometric information. Alright, now let's start with the manifold M. Now at every point P of M, we can repeat all the previous constructions of tensors for the vector space given by the tangent to M at P. In particular, we can define a KL tensor at P to just be a KL tensor of the tangent space. So for every P, we have a vector space of KL tensors at P. Now putting all of those together gives us a bundle. We call this the bundle of KL tensors on M and denote it this way. Now let's check to see if you understand. What is T01M? Well, at every P, T01 of any vector space is just the vector space itself, so this is the tangent space. Thus T01 is just the tangent bundle. And similarly, the T10 is just gonna be the cotangent bundle. Now a section of this bundle is called a KL tensor field. Actually, I lied. Not just any section, but it has to be a smooth section. And we denote the space of KL tensor fields by this curly T. Now what's the space of 01 tensor field? Those are smooth sections of the tangent bundle, and they have a special name which you might have heard. These are the smooth vector fields. But remember, previously we said that not all tensors are made equal, and we look at a specific types of tensor. Do you remember the alternating tensors? So similarly, at every point P, we can form a space of alternating K tensor at P, which are just the alternating K tensors of this tangent space. If we put these together, we get another bundle, called the bundle of K-forms. Alternating K tensor is quite a mouthful, so we call them K-forms. And differential forms are much nicer to work with than vector fields, because we can't pull back vector field, but we can pull back differential forms. And on top of that, as we have mentioned, they form a graded algebra. Thus, on a manifold, we see that we can have these families of vector bundles. However, in the definition, one thing wasn't quite clear. We claim that these are vector bundles, but we haven't given a local trivialization, so we'll do that in the next video.